We're talking about. So this is kind of an introduction, but how many of you have ever heard of that? By ever used them? Yeah, so if you're an engineer, if you've ever had to take a physics class or mechanics class or something like that, vectors are a big part. So once you understand how to manipulate vectors, actually, a big part of kind of sort of basic mechanics is done for you. So let me so a vector is basically just a matrix with only one column. We'll talk about row vectors maybe later, but for right now, we'll just focus on column vectors. So it's just a column of numbers. That's it. So let me do something more formally. So, for example, so that is an element of Rn. This symbol right here means is an element of. That means this lives in n-dimensional real space. So you've probably seen some of this. In fact, you can even take points in the plane as vectors. So examples. 1, 2 is a two-dimensional vector. And you can actually sort of represent this geometrically. This, let's see, think of this as the x coordinate. So you go over to the right of the axis 1 and then up 2. And oftentimes vectors are written this way. This is the vector 1, 2, over 1, up 2. You can have more complicated vectors. This is a vector in three-dimensional real space. So I've got to draw something on a chalkboard, so this can't be perfect. But if this is your x-axis, y-axis, your z-axis, then this vector 1, 1, 1, 1 over this way, and then 1 up. So it's kind of slanty coming out the board a little bit, right? I mean, that's sort of a terrible way to think of it, but it comes up 1, over 1, and then up 1 this direction. So vector is sort of like this. And you can do this very generally. Here's a vector in R8, which is something that we can't picture very well, but this comes up in engineering all the time. Why would you ever need 8-dimensional space? Well, I'll give you an example of that in a moment. Okay, so what does it mean for two vectors to be equal? Well, it means, first of all, they're the same size, right? So the columns are the same size. You can't have something in R2 equaling something in R3. And not only that, everything has to match, right? So the first coordinate equals first coordinate, the second coordinate, second, all. Okay. Any questions on this? So one of the powerful things about vectors, and like I say, you see this coming up in physics, engineering, robotics, things like this all the time. One of the powerful things about vectors is they actually have a mathematical structure. You can add vectors and you can multiply vectors by a constant, which is often called scaling vector. So let me tell you sort of algebraically how to add and scale things, and then I'll show you sort of what it means geometrically. Or the power of vectors is in fact add and scale vector. Let me tell you how to add first. You know, math is a tough discipline for many people. You all are kind of the cream of the crop in a certain sense. But I will tell you something that is a truism in math. Many times when people struggle with something, they make it more difficult than it is. In math, it's not easy. You shouldn't do it. Let me ask you a question. What is the easiest way you can think of to add these two vectors and get another vector that has the same number of entries?
Just add A1, B1, then A2.
That's right. Just be a total bonehead and add them up coordinate by coordinate, right? That's the easiest thing to do. So I'm going to do it. And there you go. So this is the way that we add vectors. We just add them, the coordinates separately, just add them up like regular numbers. There's also a way we can scale vectors. Let's say that I want to multiply this by a constant. So here's your vector, it's got n coordinates, and here's your c. C is just some number. Now, I need to multiply this by this and have it barf out a vector of the same size. What's the easiest thing to do?
Just multiply everything by C.
There you go. Rock and roll. And this is called scaling. So we have a sort of a magic way to add two vectors and a magic way to multiply by a constant. The vector 0, 0, 0 is called the, surprise, surprise, zero vector. Can anybody identify something that's special about the zero vector? Yeah.
Scaling.
Oh, okay. Look, you can scale any vector to the zero vector just by multiplying whatever vector by zero, and there you get it. What happens when you add the zero vector to any other vector? You're right, it doesn't change, and that's kind of a special thing about the zero. In fact, oftentimes in physics, you'll get problems like this, where you have a force pulling in this direction that's used as a vector, and a force pulling in this direction, vector, and you have to find a force that balances this. I think it's fairly easy to see how this might be important in things like balancing weights or even navigating rocket ships. You need to find a vector that balances. So if I've got a force pulling this way and a force pulling this way, and I want to put a force there that balances out, what direction do you suppose it should be? Off to the left, maybe up a little bit. Maybe a little bigger than this. Now, if this is balanced, so you're pulling here, and pulling here, and the tug of war is completely balanced, so that middle point doesn't move, what do you suppose the sum of these three vectors must add up to?
Zero.
Zero. That's exactly right. And that right there is the crux of many kind of basic mechanics problems. Yes,
When you're adding two vectors, they have to be the same dimension.
that is correct. Right. That is correct. So they have to be the same size, the same number of entries. But let me. So here's a quick example. That is a two-dimensional vector, right? And you might think of that in the plane as 1.2. Right? I could couple this with a three-dimensional vector.
You just have like a zero.
So sometimes this kind of if you want to think of it that way. Let me give you a quick example here. Let's let B equal vector. Well, we'll go back to 1, 2. W U is vector 5 minus 4, and W is vector let's say 3 minus 1. Find let's say 3U minus B minus 2B. Let's find this vector here. Well, so let me just kind of write it out explicitly. 3 times minus B. So this is going to be my U, this is going to be my B, and what did we say, minus 2W? Okay, what was U? U was 5 minus 4. B is 1, 2. And W is 3 minus 1. Everybody okay so far? Let me point out that subtraction, because I think subtraction right here is really addition of the negative, right? So let me write this way. 5 minus 4 plus minus 1 minus 2. Pull that minus in there, but I scaled it. And I pulled minus in on that as well. And this is equal to 15 minus 12 plus minus 1 minus 2 plus minus 6. And now I love adding vectors up because it's pretty easy. You just do it coordinate by coordinate. 15 minus 1. So that's 15 minus the total 7 is 8. And this is minus 12 minus 2 plus 2, so it's minus 2. So that's try to get my error. Everybody agree? Okay, we can also think, of this geometrically in many, many cases. Let me give you an example. Let me do kind of an easy addition. Okay, looking at it, is that up here? Easy, right? Easy peasy lemon squeezy. So why do I do an easy example like this? Well, I want to sort of show you geometrically what's happening here. Let's break the vectors down here. Now my first vector is 1, 1. That's like here. And my second, so this is U. And my second vector is V, which goes over 1 and down 1. Everybody agree with that? Now, when I did my little magic addition, I got the vector 2, 0, right? Which is this. This thing up here. And this, although this is just a particular example, is an illustration of something called parallelogram. Notice that this thing, in this case, makes a square, but more generally makes a parallelogram. So let me illustrate the parallelogram law, which is sometimes useful when you're thinking about this geometrically. And I'm going to do this basically. If you have a vector U, and if you have another vector V, then U plus V can be obtained in the following way. Complete the parallelogram. So let me draw something that's parallel to V here. And something that's parallel to U here. Parallel, right? Better. Since it's parallel to U here. And where they intersect. Which is exactly what happened over there in our simple example, but this always works. How many of you have seen vectors before? Has anybody ever heard the adage, if you add vectors head to tail? You've heard that one before, okay. Well, it doesn't matter if you haven't, but another way to think about this is notice that this vector here, the green one, is the same as V, and so here you go head and tail like this. But that's the same as parallel. Everybody okay with it? Okay. Any questions? By the way, let me ask you this while we're thinking about the parallelogram law. Can somebody describe this process? What if I have these vectors here? What if I have U and D? What if I want how to do that using parallelogram law? Yes, sir.
scalar of -1 on U.
Okay, good. So let me ask you this. Let me ask you a silly question. What do you suppose that 1 times U is?
So
Itself, right? What do you suppose 2 times U is?
double itself.
Right, double itself, same direction, twice as long. Everybody, half of U. Half as long, same direction. Everybody agree with that? What do you suppose minus U is?
Basically opposite direction.
That's right, same length as U, but in the other direction. So let me try to do that here. Maybe right this. This is minus U. Everybody okay with that? And now that I've got this, all I have to do now is add V and minus U. So this thing right here should be the. Everybody okay? All right. Good. Let me ask you a question. Just for fun. So I've drawn pictures of the parallelogram law. Can somebody explain to me why this works for more than just 2-dimensional vectors? Right? I mean, so I think this parallelogram law, does this only apply to R2 for 2-dimensional vectors or just apply for more? Actually, the parallelogram law will apply to any 2 vectors, no matter how big the space is, no matter how many. Do I know why? That's essentially it, right? Because no matter how many dimensions, so here's a vector in 3 space, right? Because we're all in 3 space. And here's another vector right here, right? These 2 vectors sit in 3 space, but if I only look at those 2 vectors themselves, they sit in a plane, right? So this is as general as you want it to be, right? Can anybody think of an incidence that you might have in applications where 4-dimensional? I mean, I understand 2-dimensional vectors, or at least I think I do. There, I threw some on board. I sort of understand 3-dimensional vectors because it takes 3 dimensions to describe our world. Somebody could describe a situation where you might need 4-dimensional vectors. Yes.
So you're dealing with time.
Okay, there's that. Or you could be like a string theorist and think that you need like 10 or 26 dimensions or something like that. But I can do something that almost every engineer might encounter. Now imagine 2 boats on the ocean. And maybe you have some engineering problem where you always need to keep track of where both of these boats are simultaneously, because maybe they're in communication and they're trying to fight each other, who knows what else, right? How many what's the dimension of the vector that you need to describe both boats? Here's boat A, and boat A can be anywhere in the ocean. And here's boat B. B can be anywhere in the ocean. How much data do you need to describe where both boat A and boat B are? Yeah,
You need 4 total points if you're doing it in 2 dimensions.
that is correct. Because to know where both of these boats are, you need an X coordinate and a Y coordinate to describe A. So you need a 2-dimensional vector to describe A. You need an independent 2-dimensional vector to describe B. So to describe them both at the same time, you need 4 items of data. you need a four-dimensional vector. And in fact, if I put, instead of, if I only need to keep track of 2 boats, if I need to keep track of 10 boats, all of a sudden, you're in 20-dimensional space. Everybody agree with that? Because you'll need 2 coordinates for every boat. This also comes up in, for example, when you're, when you have like robotic arms, you know, like the handle, you know, the Homer Simpson plutonium and all this, you have these arms. If you need to describe where all the joints are and how they can sit in space, this often requires a large number of dimensions. Okay, let me give you any questions. Okay, so let me give you some important properties of that in RN. So here's my ground rules. What U, V, W, V, and RN. Remember what this symbolism means. This means these 3 things live in RN. So these are n-dimensional vectors. And we will let A and B well, let A and B be real numbers. We sometimes call them scalars. So a lot of this is stuff the lawyers make you write. First observation, doesn't matter what order you add vectors in, you get the same answer, right? And if you think about how we add vectors, we add them coordinate wise, and it doesn't matter what order you add numbers. It's the same thing. So U plus V and V plus U is the same thing. If you had to add 3 vectors up, 3 in a row, say, you can add U and V first and then stick on W, or you can add U to V plus W, it doesn't matter. No surprises here, I don't think. This notation means the 0 vector. That's the vector that's all filled up with zeros we spoke of earlier. What happens when you add the 0 vector to any vector you get? You get it back. And here I'm interpreting this as -1 comes back to you. Yes.
Why would you add the 0 vector to something if it's always going to be the same thing?
Well, it's not, this is not something that I'm going to set out to do. But what happens often is that you show that some vector that you added to it is 0 vector, so therefore everything's left alone, right? When you add a vector to its opposite, it's negative, you get the 0 vector. 5. Anybody want to guess what this is going to turn out to be? When I take a number and multiply times U plus V, I get
U plus A.
very good. That's right. So this kind of distributes out. It's scaling the first, scaling the second, and adding them up. All right. There's a similar kind of thing here. Number plus number times vector is number first scale, second scale. If you take A times BU, this is the same thing as the number AB times U. And finally, I believe, the number one comes the vector u. And this one will be your book, and I'm gonna just add this one in just for clarity, because actually this last one follows from the previous ones. The number zero times u is the zero vector. So if you multiply if you scale any vector by zero, you get zero. Okay. Questions? All right. So now I want to talk about something very important in the vectors. And we're going to connect it up with linear equations, systems of linear equations again. Okay, so I'll just span and linear. Okay, let's suppose B1, B2, B3. Suppose I have this collection of vectors in R, right? I'm good. Yeah, I'm good on my slides. No problem. So suppose that we have these k vectors in Rn, and these are a bunch of numbers, A1, A2, all the way up to AK. They're just numbers in R. Then A1, B1, A2, B2, AK, BK is called a linear combination of vectors. Oops. B1, B2. So in other words, picking these different numbers, you can pick these different numbers to be anything, so you can get all kinds of linear combinations. The set of all linear combinations of B1, B2, BK is called span. And I will often write it this way. So the span of a collection of vectors is just every single possible linear combination that you can get. So let me ask you this question. I don't care what vector, which one. The one vector is always going to spin. Right? This is zero vector, right? Everybody okay with this? Because all you gotta do is choose all the numbers to be zero. Everybody agree? So no matter what vectors I pick out of thin air, the zero vector is always in their span. Let me make a couple of observations about the span of this. Each individual one of these vectors, V1, V2, all the way up to VK is in the span, right? For example, V1 is in the span just by picking A1 to be 1 and the rest of the numbers to be 0. VK is in the span by picking all the numbers to be 0 except for AK, which I'll pick to be 1. V1 plus V2 is in the span, and so on. Play okay. So, the span is just every possible way that you can multiply those by scalars and animal. Let me answer this. Okay, let's just take a. Yes,
Can I answer that?
I'm sorry.
I was gonna ask if I can answer.
I can't quite hear you.
Oh, can I answer that?
Okay, yeah, sure.
It's infinite, right? Because you can make any linear combination of any by scaling it.
Right. So, in fact, I can give you sort of a formula for it. What is a typical element of span? Notice, lucky me, I've only got one vector here, right? So it's basically all multiples of this vector. So span of 1, 1 is just everything that looks like this. So it's every vector that can be this way. So it's the set of all of them. It's right here. So the span is just all vectors that have an equal x and y coordinate. Everybody agree? Anybody describe this geometrically?
Line magnitude 1, y-intercept 0.
Here's the original vector, 1, 1. Right, that's the original. Well, the span has every multiple. Right. So it's got 1 times this vector, so there it is. It's got 0 times this vector, so there it is. It's got twice this vector. It's got 3 halves of this vector. It's got -1 of this vector. What happens when I fill in all possibilities? It's a line. Span of this vector is just actually the line y equals x. How about this? And part 3. What? The same. 1, 0, 0. 0, 1, Well, let's see what it looks like, shall we? What does a garden variety element span of these two look like? Well, it looks like A times the first vector plus B times the second vector. Do I agree with that? So I can kind of consolidate this, can I? Everybody agree with that? So what does a typical vector look like in the span of this? It can have any first coordinate, call it A. It can have any second coordinate, call it B. But what about the third? Always got to be zero. Everybody agree with that? You might describe what this looks like in free space. Yeah,
Yeah, plane. It's essentially like a two-dimensional, like they build all of the points in and then don't have like.
that's right. So let me do my crappy three-dimensional drawing again. A typical element of the span of this, well, basically, it can be any point in three-dimensional space with the caveat that the z coordinate has to be zero, right? So you can't go above and you can't go below, so it's actually this entire plane. The XY plane. Here too, but it's this flat plane that's coming out of the board. Right, okay. Okay. Here is and as I promised, here's kind of a motivating example of this last theorem that I'm going to give you today. Here's a question. Is the vector 1, 8, 9 in the span of 1 minus 1, 3 and 2, 1, 2. What are the chances this is true without using random? I mean, I actually made up notes for the class, right? If I just pick random numbers here, the vectors, what are you supposed to chances are that this actually is in that span? Pretty low. They're pretty low, right? Can anybody explain why it would be pretty low? What dimension space are we in here? Three-dimensional space, right? What do you suppose the span of these two vectors looks like, given our previous examples? What do you suppose the span of two vectors in three spaces? A plane, right? Everybody agree? And in fact, it doesn't even have to be a plane. It could be worse. It's like, what else could it be? Two intersecting planes. Well, right. So let's suppose that the two vectors are pointing in the same direction, then it's just going to be a line. Everybody agree? Which is worse, right? So if it's a plane in free space, what are the chances that I've actually picked a point that's on that plane? Seems pretty slim, doesn't it? Right? Is this on there? How can we tell? Well, the best thing to do with a problem like this is just like REM on their monster album, you got to go back to the roots here and ask yourself this: self is 189 in the span of this. So try to solve. X1, 1 minus 1, 3, plus Y1, or X2, 2, 1, 2. If I can solve this, that means that this is in the span of those two. If I can find an X1 and X2, there are solutions there. Everybody okay with that? So let's try it. And you know what this is? This is actually three equations and two unknowns. This is x1 plus 2x2 is equal to 1, minus x1 plus x2 is equal to 8, and 3x1 plus 2x2 is equal to -9. Everybody see how those connect? So really, it's taken us back to what we've done before. Let's do that augmented matrix stuff and see what shakes out. Let's see. Let me make my matrix here. 1, 2, 1, minus 1, 1, 8, and 3, 2, -9. Let's see if this sucker has a solution or not. Well, I'm going to use this 1 here. Take out the rest here. 1, 2, 1. Just straight up add 0, 3, 9. And I'm going to multiply this by -3. Take that out. That was -3, so that's going to be -4. -3, -9 is -12. And I can clean this up a little bit. It's 1, 2, 1, 0, 1, 3, 0, 1, 3. Okay. Multiply, dividing out. And so this is going to be 1, 2, 1, 0, 1, 3, 0, 0, 0. We have a theorem from last time that tells us this is consistent. Right? Because you don't, so this, look at your rows where the variables are 0, like this one, that's 0. So that means no interference, could be consistent. And here's what we have. We have x2 equals 3 from this equation. And we have 2x2, well, now we have x1 plus 2x2 is equal to 1. So x1 -5. And so the answer is yes. This actually is in the span. And what it tells me is -5 times this plus 3 times this should be my resulting vector. So let me make a final observation for today. And again, this is important because this theme will come up again in conjunction with our linear equation. A vector approach. And I'm going to write it this way: x1, b1, x2, b2, plus xk, bk, b. And by the way, I'll try to distinguish when I don't have a hat on it, it means a number. And when I have one of the little hats on it, it means a vector. Notice that this is just like, this is our vector equation here. This column here is B1, this column here is B2, and this column here is B. Has a solution, or has safety. As the augmented matrix. And when I say this equation in this augmented matrix, system of solutions have the same, when I say the same solution, that also means that this has a solution if and only if this has a solution, and if they do, so if this one doesn't have a solution, it's this. And so B is in the span B1, P2. PK. If and only if. Augmented system. P1, P2, PK. D. Okay. Any questions? Questions? All right, well, don't forget that you have to do a new tag. If there are any questions, I'll be in my office, well, as soon as I can get up there after my next class. And other than that, y'all have a good one. We'll see you on Wednesday.